Ma'am,
Yes,
ma'am, can you explain the ultraviolet rays?
yes. I will have a recap. Okay. 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 Bismillahir Rahmanir Rahim. We will talk about radiation today. We have talked about conduction and convection. Okay. What is the difference between conduction and convection? Real quick. What is the difference between conduction and convection? Difference. How is convection different from conduction? Use the chat window. Use the chat window. No. We're doing physics. Okay. Can you please, can anybody tell me the difference conduction in solids and convection in liquids? No, I want the molecular difference, you know, the difference at the level of particles. Okay, let me just tell you, okay, because we don't have time. Okay, conduction is due to the physical contact of atoms with each other. When one vibrates because of the physical contact, the neighboring atoms also vibrate. And conduction is also due to the movement of electrons. Electrons do not have a fixed position. They are free to move from one corner to another of the metal. Yes, and whereas in convection, it is important to mention that convection is the movement of fluid, not just liquid. Fluid, meaning we are also including gas along with the liquid. Don't just say liquid. If you will just write liquid, it would be wrong. You have to say it is the movement of fluid. And by movement, I mean to say that the molecules leave their position and move to another place. They do not have a fixed position like in conduction. The atoms had a fixed position. In convection, they move, they leave their position, they take another position. So they do not have a fixed position. So therefore convection, and it is due to the change in density. So when I ask you in convection, what are the keywords? Flow of the fluid. Okay, the fluid is moving, movement of fluid itself, movement meaning no fixed position, and due to the difference in density, difference in temperature and difference in density. So these are the keywords. If you don't write these keywords, definition of convection will not be correct. And when you are differentiating between conduction and convection, you will mention this, that conduction is due to vibration, which is transmitted to the neighboring atoms due to physical contact. Whereas in convection, it is the fluid itself which is moving due to the difference in density, which in turn is due to the difference in temperature. Right, okay. Now we move on to radiation. In the last class, we briefly discussed that radiation is the third mode of transfer of heat, which does not require any particles, and therefore it can take place through vacuum. Okay, now heat, when we say heat is, what was heat? Does anybody remember the definition of heat? Okay, all these definitions that I tell you, you have to remember them. I'm not asking you to ratify, but you should remember the main concept. What was heat and how was it different from thermal energy? Good job, Myra. Yes, Ariba, good job. Part of thermal energy that flows, right? So the difference between heat and thermal energy is that thermal energy is the sum of the kinetic and potential energies of all the particles, whereas heat is part of that thermal energy which flows. Okay, so we have discussed this previously. Now, when we talk about heat, which is the flowing thermal energy, we are talking about these three parts of the electromagnetic spectrum, because heat is a part of electromagnetic wave. It is an electromagnetic wave, right? But the heat that we are dealing with is predominantly visible light, some part of infrared, very little part of ultraviolet, very little. Okay, predominantly, mostly it is this visible light spectrum, which are these 7 colors. I hope you have done this electromagnetic spectrum in grade 5, 6. I think in grade 5, I remember. So these are the 7 colors that we see. So this is the visible light. This is visible light. Okay, and then a little part of infrared and extremely little part of ultraviolet. Okay, so when you move from gamma rays all the way towards this end of the electromagnetic spectrum, which is radio waves, you can see that the wavelength is increasing. Wavelength is increasing and frequency is decreasing, because all of these waves have the same velocity, which is 3 into 10 to the power 8 meters per second. This is one of the properties of electromagnetic waves. All of them travel at a speed of 3 into 10 to the power 8 meters per second. So if velocity is constant, then frequency is changing and wavelength is changing. So when this increases, this decreases, and vice versa. When frequency increases, wavelength decreases to keep the product constant. Product is the velocity. Product is the velocity, okay? So I hope you got this point. Now, I also talked about the third property of electromagnetic waves is that when they hit a substance or when they hit any surface, there are 3 fates. What happens to them? The 3 things can happen to them. Fate means what can happen to them. Either they can be reflected, like bounce off from the surface, or they can pass through that substance, which will be called a transmitted ray. By the way, transmission only happens through transparent or translucent substances. So a transmission will only be if the substance is transparent or translucent. Otherwise, only reflection. And this is the third fate, which is absorption. So there are 3 possibilities. When an electromagnetic radiation hits a surface. Now, by electromagnetic radiation, I mean what? I mean light as well as heat. Because what did I say? That heat has these 3 parts: light as well as little of infrared. By the way, warmth is this infrared. See, you cannot see warmth, right? You cannot see heat. Why? Because it is infrared. It is not a part of the visible light. When there is enough energy, as you move, as you give more energy, see, energy is increasing this way. Because remember, energy is the product of this constant and frequency. So as frequency is increasing, energy is increasing. So as we increase the heat, first we have warmth, just simple warmth. Okay, like a cup of coffee would be warm, right? So that would only be radiating infrared rays. But if you increase the temperature, then you start seeing red hot. If you keep increasing the temperature, a time will come when you will see yellow, blue. These are the colors of flames of fire, if you remember. The flames of fire, you see yellow in the flame, you see blue in the flames, sometimes you even see green in the flame, violet in the flame. And then a time comes when all these colors combine to give you white hot. Okay, and if you keep increasing, then you know that also has ultraviolet. Okay, a little part of ultraviolet, but ultraviolet is not too much. Okay, so this is what I mean. So this can be light with heat, or this can be just simply heat. Okay, it depends. Now sunlight also has all 3 parts. Sunlight also has infrared, visible light, a little of ultraviolet, right? So if we are talking about sunlight, so let's talk about sunlight. If this is sunlight, then sunlight would also have infrared, visible part, and ultraviolet, and it can have these 3 fates. What are the 3 fates? That it could be either reflected, okay, transmitted, if the substance is translucent or transparent, or absorbed, right? Okay. Now, what will decide, what factors will decide what would happen to these electromagnetic waves that are falling? Should they be reflected? Should they be absorbed? Should they be transmitted? Now, transmitted we know depends upon the transparency of the substance. But let's not talk about transmission, okay? For now, we will not talk about transmission. We will only talk about reflection and absorption. Now remember, reflection and absorption both cannot take place equally at the same time, because the incident rays meaning rays that are falling, the incident rays have to decide. If there is more reflection, there will be less absorption. If there is more absorption, there will be less reflection. There's like sort of division. Okay, I have made another diagram to clarify this point a little more. Let me show you that diagram. Oh, where did that diagram go? Okay, here it is. Like, for example, look at this surface. All the rays that are falling are getting reflected, right? So very less is getting absorbed. Let's suppose there are 7 rays, 1, 2, 3, 4, 5, 6, 7. Out of 7 rays, this is just for explanation, okay? This is just to make you understand the concept. So out of 7 rays, 6 rays are getting reflected. Why? Because this is a very good reflector. Let's suppose we'll talk about which sort of substances are good reflectors. But just understand that those surfaces which reflect really good absorb really less. And another thing, out of these 3 fates that we just discussed, which ray contributes towards the increase in temperature of the substance? Now, reflected ray just got bounced off. It will not increase the average kinetic energy of the particles. It is just simply reflected away. It will not increase the temperature of the object, okay? It will not increase the object, or it will not warm up the object. Now, transmitted, we're not talking about it, and it will also not contribute towards the increase in temperature. But it is this absorbed ray. It is this absorbed ray which will increase the average kinetic energy of the particles, because it is absorbed by the particles. This is the heat that we talk about. It is that thermal energy that flowed in, okay? So this is heat. This is what increases the temperature. This is what increases the average kinetic energy of the particles, okay? So when a substance reflects most of the rays away, that means very less rays are absorbed. Out of 7, 6 rays got reflected. Only 1 ray was absorbed, and it contributed towards warming this object up. So therefore, this absorbed less energy because most of it got reflected away. And therefore, the temperature will not rise that much. Temperature will stay, almost the same, or, maybe increased a little bit. Now look at a rough surface, or let's suppose a surface that is not reflecting very good. Okay, it is not reflecting very good. And so out of 7 rays, only 3 rays got reflected, and the rest of them got absorbed by the atoms or by this substance. And therefore, this absorbed thermal energy is greater because more rays got absorbed. And so more thermal energy will be gained by this substance, and so temperature rise will be greater, right? Now, another thing that you should keep in mind, whatever, okay, temperature rise I cannot say, but yes, it absorbed a lot of energy, okay? But because, these are insulators, so maybe, they are not conducting well. So, but it absorbed a lot of thermal energy, okay? Now, whatever it absorbed, the same energy will be radiated, okay? Whatever is absorbed, out of that absorbed energy will be radiation. I did not make radiation. Let me make radiation here, okay? So if, for example, let's suppose 4 rays got, I mean, this is only for your explanation purposes. If 4 rays got absorbed, let's suppose out of 4, 3 got radiated away. Okay, this is radiation. Okay, by the way, radiated rays, you will always make radiated rays curly, not straight lines, because the straight lines are representing light. Straight line, remember, will represent light. In your diagrams, if you want to show radiation, always use these curves, curvy lines, okay, like this. So yeah, very small curvy line here, because why? This will not radiate because it already absorbed 2 less. Because it absorbed 2 less, out of that, a fraction of that would be radiated. Why isn't the whole of this energy radiated? Because some will be used in the vibration of the particles. Some will be used in the vibration of the particles, and so whatever will be, you know, extra, that will be radiated away. So remember that. So radiation will be less than what it absorbed. Part of it will be part of it, right? So it makes sense. Things that absorb good will radiate better, right? Things that do not absorb at the first place, how can they radiate away? Right? Because they never absorbed at the first place. Then how will they radiate away? So good absorbers are good radiators. Bad absorbers are bad radiators. And it happens that good absorbers are bad reflectors. It happens that good absorbers are bad reflectors. And bad absorbers are good reflectors. Or you can say good reflectors are bad absorbers. Why? Because most of the energy which is falling on their surfaces is getting reflected. It is not getting a chance of being absorbed. And so that energy is not, you know, being gained by the particles of that substance. And therefore that object does not have enough energy to radiate. I hope I made sense. Okay, now another thing. Most of the good reflectors are shiny surfaces or smooth surfaces. How do you know if a surface is smooth or not? How do you know? By looking, by observation. How would you know if a surface is smooth or not? Do you know? Do you know? Yes, good job. Shiny, yes. A shinier a surface, the smoother it is. Okay, smooth surface. When do you get shine? What is shine? Can you zoom out? Zoom out. Yeah. When do you get shine? Shine is due to this regular reflection. Can you see the difference? And now zoom out. I want both the diagrams together. Okay. Yeah. Okay. Look at the difference. This is called regular reflection. This is regular reflection. And this is irregular reflection. Okay. When you, what do you mean by regular reflection? Can you see all the reflected rays are parallel to each other? When all the reflected rays are parallel to each other, this is called regular reflection. When the reflected rays are haphazard in different directions, going in all different directions, this is called irregular reflection. And this is what happens on rough surfaces. And this is what makes surfaces look dull. So when, for example, this paper is not shining, right? Because the surface is irregular. You can consider the surface of paper this way. The particles are a little farther apart, though this is solid, but a little farther apart because there are air spaces between them. Okay, this is like an insulator. The surface is rough, you can see. And so the incident rays are falling at different angles and getting reflected at different angles. This is what is making it dull. This is smooth, shiny surface, and most of the shiny surfaces, not necessarily, but most of the shiny surfaces are metals. Well, you have glass also, that is also shiny and smooth. Surface of water, smooth, shiny. And you have mirror, glass, right? Smooth and shiny. Now, the shiniest substance, the shiniest surface, I think, on the face of Earth is mirror and water surface. If you have seen a clean water pond with no pollution and the water is clear and the surface is calm, you can see the reflection of a sky on it. That is an evidence that the surface is absolutely smooth, and whatever rays are falling on it are getting reflected. This regular reflection is responsible for images being formed on mirrors on the surface of water. So these surfaces do not absorb at all. They simply reflect 100%. Whatever rays are falling on them, 100%, almost 100% reflection. Okay, not absolutely 100%, like almost 99 point something percent reflection. Okay. Okay, and that might be another reason why water does not get uh, warmed up easily by the sun rays. Remember, we were discussing that yesterday. So this tells us that dull surfaces are good absorbers and dull surfaces are bad reflectors. Irregular surfaces are good absorbers and irregular surfaces are good reflectors. Okay, another thing. Why do you think irregular surfaces might be good absorbers? Because another thing, irregular surfaces, if you pay attention to the surface, has greater surface area compared to the smooth surface. Okay, if I straighten this line up, you will see this line would be longer than this. If I straighten this straighten this line up at the surface, this line would be longer than this if I straighten it up, right? So that shows this surface area is more. And remember, transfer of heat from one medium to another takes place across lose heat faster. So whatever the transfer of heat is in whatever direction, it would be faster in a rough surface as compared to smooth. Okay, because of a greater surface area. Okay. 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 So I made this table. Dark surfaces. Why does anything look dark? Substances look dark when they are absorbing most of the colors. Substances look dark when they're absorbing most of the colors, right? And they are shiny when they are reflecting everything. So shiny substances are bad absorbers. Reflectors, dark are absorbing all of them, so reflection is less. Okay, shiny are good reflectors. Now emitters, now remember, emitter is just another word for radiator, same thing. Radiation, emission, same thing. Okay, you can call them radiators or emitters, same thing. So whatever absorbed, emitted. Yeah, because where did the radiation come from at the first place? They absorbed first, right? So good absorbers will be good emitters. Bad absorbers will be bad emitters. Okay, I hope that point is clear. I will take questions from you if you have any, but let me finish this first. Okay, this is the definition of radiation. Radiation is the flow of heat from one place to another by electromagnetic waves. Okay. Let me see. Is there any point I missed? Okay. Okay. Yeah, I think I have. Yes. Okay. Yes. One point I wanted to tell. Right. Now, I just mentioned that most of this warmth that you feel, even coming out from our bodies or from any warm substance or any substance at all, is in the form of infrared radiation. If you increase the energy, it will turn into visible light and then also a little part of ultraviolet. Okay? Any substance which is above absolute zero. Now, this thing is written in your book. This thing is written in your book. Any substance, the temperature of which is above absolute zero, will emit infrared radiation. Now, right now, my body is emitting, and your body as well, is emitting infrared radiation. Okay, what do you understand by this absolute zero? Does anybody know what absolute zero is? Does anybody know what absolute zero is? Oh, where is it talking about? Here, look at this. On this page, page 102, radiation is emitted by all bodies above absolute zero. Let me see if you guys know it. Okay. Coldest possible temperature of minus 273 degrees Celsius. No movement of molecules. Okay, good job. We see colors because that substance absorbs all of the light spectrum except the one you see. Yes, yes, okay. Kelvin temperature, yes, absolute zero is in Kelvin scale, as there are many substances which have different colors. So like what makes the colors different? Since the same substance is supposed to absorb the same amount of light. It's not about the amount of light, Sarah. The color depends upon which wavelength is getting reflected. Wavelength. Okay, this electromagnetic spectrum that I just showed, this electromagnetic spectrum that I showed, the color varies with wavelength and frequency as well. Okay, so as you're moving from red to violet, the frequency is increasing and wavelength is decreasing. Isn't the same substance supposed to send the same wavelength? No, no, no. Or if white light is falling, then that means all the 7 colors are falling. Out of those 7 colors, that substance will absorb the rest and will reflect only the color that you see. Okay, emitters are of dull colors. Okay, what I'm trying to, yeah, I will come to absolute zero, but students are asking questions. I'm trying to answer their questions. When the atoms do not vibrate at all, as there are many substances which have different colors. So like what makes the, will only white color reflect rays? Yeah, white color will reflect all the colors together. Okay. Okay, so yes, you guys are close. Everybody gave half answer. So together it made a complete answer, but not actually absolutely complete. There's still parts left. Yes, you are right. It is a Kelvin scale and it is minus 273. And yes, the molecules vibrate less. And yes, all of that. I think it was in one of the chapters that you guys did for assessments or maybe the midterms. I don't remember exactly. But yes, absolute zero is this. I made this little so that you guys know what I'm talking about, what the book is talking about. See, this is a graph of temperature against pressure or volume. Right now, as the pressure decreases, yes, the temperature, as the temperature decreases, the pressure and volume, both of them decrease. By the way, you can have only one quantity at a time. You can observe only, for example, the change of volume against temperature or the change in pressure against temperature, but both of them will decrease linearly, meaning the graph will be a straight line. It will be linear, right? Now, you cannot have, practically speaking, you cannot have zero volume and you cannot have zero pressure either. Okay, so you know, with whatever is practically possible, you carry those experiments out and then you extend the line till it touches the 0 of the y-axis. And it happens that it touches the 0 of y-axis at minus 273 degrees Celsius, where the x-axis is temperature in degrees Celsius. Okay, so this is a hypothetical point. Hypothetical meaning this does not exist in reality. In reality, there is no, it is not possible. I mean, it wasn't possible. I don't know if they have done any recent development, but the atoms are hypothetically considered to be absolutely static and not moving at all. Well, practically speaking, it doesn't happen that way. Okay, we cannot achieve this temperature, but okay. So this is absolute 0. This is what they're talking about. So any body which is above this absolute 0 will emit infrared radiation. That's what they're trying to say, right? Okay. Now let me address your questions and then we will move on. No, not equal to 0 Kelvin. Yes, yes. Okay, yeah. 0 Kelvin. Yes, absolute 0 is 0 Kelvin and minus 273 degrees Celsius. Emitters are of dull colors, but there can be radioactive shiny substance. Example of white hot is magnesium burning, right? Yes, might be. Yes. Okay. Let's move on to the vacuum flask. Right. Right. Okay. Okay. Another thing. Okay, I forgot to mention this. On the back of refrigerators, you know what the refrigerator is doing is it is sucking the heat out from its inside, right? Because the food is kept in inside, and so what the engine of refrigerator is doing is sucking the heat out and is throwing outside, right? And so in the process, the engine gets warmed up, right? So we want to lower the temperature of the engine because otherwise the engine might be damaged, right? So we want a substance that can absorb good and can then radiate it out. Because if it cannot radiate, then it will itself get too hot and it won't be able to absorb anymore. So it should be good absorber and good emitter. So that is why at the back of the refrigerators, we have these black fins, because black is a dark color and it is good in absorbing and good in radiating out. And that's why we have those black fins at the back of the refrigerator. Have you guys seen it, or you want me to show it to you? I got a picture of it. Let me share my screen. Okay. Here, these are the fins, these metallic bars, okay, crisscrossing the back of the refrigerator. So they absorb the heat and then they radiate it out, right? Okay. Now, these are experiments mentioned in your book, how to compare the absorption of different surfaces. A dull black surface compared to shiny surface. Now, you can see that how they have designed this experiment in such a way that they have kept all the factors constant except for the color of the surface. Rest of everything is identical. Same material, tin, same wax, same coin, and there's an electric heater in the middle. So electric heater is radiating its heat out equally in all the directions. And so both the surfaces are receiving equal heat, but they differ in their surfaces. One is dull black, the other is shiny surface. So which one will melt? Which coin will come off first? Yes. Which coin will come off first? Yes, the dull one. Good job. Yes. Okay. Yes, wax on the black surface because it is absorbing more and therefore temperature is going up faster, and so the coin is coming off first. Okay. Then there's this other picture here comparing emitters of radiation. So same copper sheet, but it is polished on one side and it is blackened on the other side. And then using the backs of your hands as sensors, they are sensing the radiation, which surface is radiating better. So yeah, this is not accurate because you are using your hands as a sensor, but yes, it is a pretty good, it is, I mean, it's okay for our purpose, it will give us an idea. And because if the person is the same, I mean, both hands belong to the same person, they can very well compare the difference. Okay, so the blackened surface will feel hotter, right? Now let's move on to the vacuum flask. Let's see, okay. Okay, right. Let me get back, okay. Now I made this vacuum flask diagram for you guys. Now, let's look at now. Vacuum flask is used to keep liquids, hot liquids hot and cold liquids cold. So the purpose of this object is to prevent heat transfer. Heat should not enter and heat should not leave, right? That's the purpose. So what have they done? Now there are three modes of transfer: conduction, convection, and radiation. All three should be prevented, okay, because we want to keep the temperature of the liquid whatever it is: conduction, convection, and radiation. Right. First of all, let's start with the cap. Okay, the cap is made up of plastic. It is an insulator, so will not allow any conduction, right? And then we have this outer plastic case. This is also made up of plastic. Again, it is an insulator. Okay, will not allow any conduction of heat out to the air molecules. Then we have the silvered double-walled vessel. Silvered double-walled vessel. Now, and then there is vacuum between the two walls. Okay, what modes of transfer is vacuum preventing? What modes of transfer out of these three modes of transfer, which two are being prevented by the vacuum? Yes, it can be made up of glass. It is made up of, usually it is made up of glass, right? And again, glass is an insulator. So if it is made up of glass, that is an insulator. Yes, thank you very much, Amna. But in recent vacuum flasks, they are using other substances as well. But yes, glass. Okay. So what modes of transfer is being prevented by vacuum? No, I don't think aluminum is a good idea. Aluminum is a pretty good conductor. It's a very good conductor. It's used in power cables, remember? We don't want that here. Okay. Vacuum is preventing which two modes? Yes, conduction is one of them. And yes, Ajwa, good job. Yes. Because conduction and convection are the two modes of transfer which require some medium. They require particles for the transfer of heat. So vacuum will prevent conduction and convection, not radiation, because radiation can take place through the vacuum. Right. So conduction and convection are only prevented by vacuum because they require a medium. They require particles, right? Now, what to do about radiation? Out. And yes, and then this stopper is also preventing convection. It is reducing convection. Why? Because there is not, first of all, the stopper is also preventing evaporation. Because remember, if the liquid is uncovered, there will be some degree of evaporation, even if it is cold. There will be some, I mean, if it's cold, evaporation will be less, but yes, there will be some evaporation. So stopper is also preventing evaporation. And by the way, evaporation was also one mode of transfer of heat. Okay, yes. And then stopper is not allowing the warm air to establish a convection current. If the warm air rises, it has nowhere to go. It is pushed back. It is pushed back, right? Or it will condense back into the liquid. So it's not allowing those convection currents to be established here. There's not much space here. So convection is being prevented. And because of vacuum, again, there can be no convection here, but there will be little radiation. Now that radiation can be prevented by the silver lining. You know, I'm shading this. This means that this surface is lined by silver. I mean, these are silver surfaces. So if any heat tries to, or is, you know, trying to get conducted through the surface, will be radiated, or it will be reflected back. Because remember, shiny surfaces are good reflectors and bad absorbers. So they won't absorb, but the heat will get reflected back into the liquid. Okay, so that will prevent the heat from getting out. And in case of cold liquids, if outside heat tries to get in and somehow manages to reach the surface despite this plastic insulator, that will also be radiated back to the outside environment. And so there is this barrier that is difficult for the heat to pass through, right? Now, we cannot say that this is 100% working, but yes, it works pretty good. It can maintain the temperature for a couple of hours. I mean, yeah, quite a lot of hours. But eventually, of course, if you have made tea in the morning and you check the thermos at night, eventually, after so many hours, there is loss of heat. But yeah, so nothing is 100% perfect. Okay. Any question regarding this? And then I will move on to the greenhouse effect. AC has the same case like refrigerator. I don't know. Go ahead, check out. Okay. Yes, good job, Amina. Yes, even if it evaporates, it condenses and falls back. And so whatever little convection current might see, convection current is more influential if the current is bigger. Okay, if the currents are small, really small, then the loss of heat is not that much. So because of the small space, because of the small size of a space, I don't think the convection current are big enough for a substantial loss of heat. But yes, as I told you, if you leave the liquid for, you know, extended periods of time, such as the whole day, then of course, you know, all these minor losses of heat would add up, and eventually the liquid would come to thermal equilibrium with the environment. What does thermal equilibrium mean? So many layers. That's why it looks big from outside, but yes, but actually the capacity is not that much. Yes, because of so many layers, right? And then why does slight conduction is lost? What do you mean slight conduction is lost? See, all of these methods of preventing heat loss are working pretty good, but they're not 100%. Okay. Okay, let's, Myra, is there any question you want to ask? I did not understand your question. Why does slight conduction is lost? What are able to escape? Molecules, you mean? You mean water molecules? No, I don't think water molecules will be able to escape because of the stopper. Okay, if you remove the stopper, then okay, let's move on to greenhouse effects. Now, okay, thank you very much, Ibrahim, for sharing your knowledge. Okay, now this is my greenhouse. Okay, now this is the sunlight, and these are the rays which are falling on. And now greenhouses are made of this special glass, or you know, the covering. I don't know what material this is. You can find out, but this lets these rays fall. Okay, now I told you sun rays have this visible part, little of ultraviolet, and then yes, of course, infrared as well. Okay, now they have some particular wavelength and frequency, whatever. Now they can enter, right? They are entering, and now they are getting absorbed by these plants or whatever is inside the plant, whatever is inside this greenhouse glass, right? Now, as I told you, that as the substance is absorbed, where did my diagram go? My diagram, yes, here. As I told you, that as the energy gets absorbed, part of it gets radiated, only part of it, not 100%. I mean, if for example 4 rays got absorbed, you won't get all 4 out radiated, because some of it is also used by the particles vibration, right? Part of it, a fraction of it, will be radiated out. So same is the case here. When the plants absorb these rays, part of it is radiated out. And of course, some energy is used by the particles themselves. Okay. And remember, they also trap, right? For photosynthesis, the chlorophyll in them traps, and so energy is used by these plants. So the energy, the leftover energy which they radiate out, which they are not using, has less energy, and therefore longer wavelengths. Remember, as the energy is decreasing, wavelength is increasing. As the energy is decreasing, the wavelength is increasing. So because the leftover energy is less, because the plants use them and the particles are also using them for vibration, and they're using for photosynthesis as well, therefore the energy which is, so the energy which is radiated out it has less energy and therefore longer wavelength. Now this long wavelength rays cannot pass through this greenhouse glass or whatever this is, okay, this greenhouse glass. And so these rays are trapped. A lot of long wavelength rays will be trapped here that will eventually increase the temperature, increase the ambient temperature of the air inside this greenhouse, which these plants use. This temperature is good for their enzymes and for their growth. So their enzymes, remember, enzymes are temperature specific. So they require that optimum temperature for their best working. So that is why this temperature is given to these plants for their better growth, especially in cold countries where it is snowing most of the times. And when they want to grow plants, they have these greenhouse, they have these greenhouses. Also, the atmosphere, which is surrounding our planet Earth, also behaves in the same way, behaves just like this greenhouse glass. Okay, again, the incident rays. Now let me make another diagram for that thing. Thank you. So this is the sun, okay, and again, so this is, for example, the planet Earth, right? This is the atmosphere. So atmosphere is, is like a big protective ball around the planet Earth. Okay, so this behaves like a greenhouse glass. So the rays enter and then they're absorbed by the earth and all the plantations on the earth and whatever is on the earth. And so the rays that are radiated out are of longer wavelength, which cannot exit out of this atmosphere. And so they get trapped. And so the temperature of earth is maintained, right? So why is this important? And what are the gases which contribute towards this greenhouse effect? And what do I mean when I say that there are some gases that contribute towards these greenhouse gases? Is that gases like carbon dioxide, gases like methane, these are greenhouse gases because they are the ones which get affected by the sunlight and by the sun rays, and they are the ones which prevent these wavelengths from getting out. Now, other gases like oxygen, nitrogen, they don't care. They are not responsible for blocking these long wavelengths. Only these greenhouse gases, by the way, water vapor is also one of them. Water vapors, methane, carbon dioxide, and also chlorofluorocarbons. This is pollutant. This is a pollutant. So this also behaves as a, these are all greenhouse gases. Okay. So why was this important at the first place? This was important because if there was no atmosphere, the rays which are falling on the sun would be, most of them would get reflected back. And so the temperature would be too low to maintain life. In order to maintain temperature, which is essential for light, the greenhouse effect of the atmosphere was required, right? Okay. Yes. Okay. So we have talked about the greenhouse effect. Any questions? Okay. Maybe nitrogen dioxide as well. Yeah, maybe. I'm not sure. Yes. Ozone layer, same as greenhouse gas. Maybe. Yeah, I'm not sure. But let them enter the rays. Okay. 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 Let's move on to, what is that? When more heat is trapped, glaciers melt and the water levels increase, and so cities near water bodies are at risk of immersion in water, like New York. Yes, like New York, Florida. Florida, number one. We have problem of lack of water. They have problem of excess of water. So much so that they're drowning. And we are scorching here. Okay, let's talk about the rate at which object loses heat. Okay, this last part of your book, I'm trying to discuss this. Rate of cooling of an object. Remember, rate of cooling or rate of gaining heat, same thing. Okay, if the pathway for heat entry is easier, the pathway for heat exit would also be easier, right? Now, why? And I talked about the surface area, remember here, because the heat exchange actually takes place at the surface. So greater the surface area, more molecules are in contact, and so they will conduct easily, remember? Now, your book is explaining this in the calculating way, you know, in the way of calculation. So let's do it that way. Okay, it's interesting, by the way. Rate at which object loses heat, and I would also see, no, you don't have to learn these formulae. This is only for understanding. Appreciate, just appreciate and understand. Rate at which object loses heat or even gains heat, same thing. Okay, let's talk about it now. Rate of heat transfer depends upon surface area to volume ratio. Okay, rate of heat transfer, gain or loss, can be either way, directly proportional to surface area to volume. How? For example, this is a cube, and you know cube has all surfaces perfect squares. Okay, all surfaces are perfect squares. And how many surfaces do we have? 1, 2, at the bottom 3, 4, 5, and then at the back 6, right? 6 surfaces. And the area of one surface is L square. Are we convinced? The surface area of one, the area of one surface is L square, and we have 6 of them. So 6L square is the total surface area of this whole cube, adding the surface areas of all the sides, right? Divided by the volume. Now the volume is easy, length multiplied by breadth multiplied by height, which is L cube, right? Calculating this, L square means L multiplied by L, L cube means L getting multiplied by itself 3 times, right? So these 2 L's get canceled, and we are left behind with 6 divided by L. This is ratio. We are not dealing with units here, okay? Area, okay, this I explained to you. So this is the surface area to volume ratio of this cube, remember. You will see, Syed Nabil, you will see in the past papers when you will do past papers. So this is the surface area to volume ratio for this cube. Now, if we double the length, of the cube, okay, I did not make a bigger cube. I can make a bigger cube. Okay, this is not bigger, leave it. So just understand that the lengths have been doubled, okay? So now the area of each square would be 2L multiplied by 2L would be 4L square, right? Or 2L multiplied by 2L 6 times, because this is the area of one surface and then multiplied by 6. And then the volume would be 2L multiplied by, because length multiplied by breadth multiplied by height was the volume, right? So 2L, 2L, 2L. Are you getting me? So I calculated this. 2 2s are 4, 4 6 are 24, 24L square, 2 2s are 4, 2s are 8L cube. Again, I calculated, I canceled, and I got 3 by L, 3 over L. Now compare, now this was a bigger cube. This was a bigger cube. It was 2L, okay? And this was a smaller cube, okay? This is a smaller cube, this is a bigger cube. Can you see that its surface area to volume ratio is 3 over L? And this smaller cube surface area to volume ratio is 6 over L. So which is more? Which surface area to volume ratio is more? 6 over L or 3 over L? Which is a bigger fraction? Huh? Which is a bigger? 3 over L is a bigger fraction? Yeah, yes, 6 over L is a bigger fraction, yes. Because the greater the numerator, the greater the overall value of the fraction. If the denominator is the same, we will look at the numerator if we want to compare the fractions, right? So this, it has a greater surface area to volume ratio. So did you see that how when the size of the cube is small, the surface area to volume ratio is more? Okay, so how when I doubled the length, the surface area to volume ratio halvened. It halvened. When I doubled the length, the surface area to volume ratio halvened, because half of 6 over L is 3 over L. Okay, half of it. This is what they're trying to show. So 2 1s are 2, 2 3s are 6. Amina, this is big explanation. It's already 9 o'clock. I cannot repeat this. Just do it. Sit down. Do it yourself. Okay, and I'm also recording this class. You can listen to my recording again. Okay, I can do it again, but you know, then just calculate this again. Okay, calculate the surface areas of each side. Okay, all of this you understood. You were with me during the calculation, right? Now compare 6 over L and then 3 over L. Can you see this is double of this? Can you see this is double of this? If you multiply this by 2, you will get this. So did you see that by doubling the length, you are halvening the surface area to volume? By doubling the length, that means the smaller the pieces, greater the surface area. Why is it that when we cut something into small pieces, the surface area, they say that the surface area has increased? This is what they mean. Because the smaller pieces have greater surface area. More molecules are exposed. More molecules are in contact with the surrounding. Yes. Thank you very much, Ibrahim, for remembering. So heat transfer begins at the surface. So higher the surface area to volume ratio, faster the rate of heat transfer. I hope I made sense. Okay. Now, this is my question. This is a smaller cube. This is a bigger cube. Yes, I know, Yusra. Thank you very much. One has a thermometer, the other has a heater, electric heater. Okay, so we are heating both the cubes. They're both made up of aluminum, right? And I have thermometer here to measure temperature, and then heater is heating both the cubes up. You can see that the length of this bigger cube is twice the length of this smaller cube, right? And both of them are at the same temperature. Okay, this should be 35. Now, if both are at 35 degrees Celsius, which box will cool down faster? And can you plot a graph of temperature against time for both of them? Qaid-e-Azam, first answer my questions, please. Before asking me a question, please answer my question. Answer this question, that which of them will cool down faster? Yeah, why will it cool down? Yes, okay, you answer. You tell me, why will it cool down? Yes, Hania, good job. Yeah, after they have been heated up. After they have been heated up, good thinking. Good thinking, good job. But after they have been heated and brought to this temperature, and with the help of thermometer, we know that they are at 35 degrees Celsius. Now we have stopped heating. Okay, now we are plotting their temperature against time, and they're allowed to cool down. Okay, I did not tell you this part. Okay, now tell me, which one will cool faster, and how will you construct the graph? वाह 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 उस्मान, वाह वाह वाह, क्या बात है आपकी। मैंने इतनी मेहनत की और आपने जाना। Yes, Hania, your answer is correct. And Aisha Nadeem, your as well. Smaller one. Arham, good job. Yes, why? Ajwa, the larger box will cool down faster. The smaller cube will have a steeper curve. Good job, Aisha Nadeem. Heated smaller first, large cooled first. जो heat पहले करेगा वही cool भी पहले करेगा. Because I told you, if a substance gains heat faster, will lose heat faster. It goes both ways. Okay, Amna? Okay, I just showed you that the smaller cube, look at the video. I just showed you that the smaller cube has a greater surface area to volume ratio. Greater the surface area to volume ratio, meaning cooler, faster cooling. This has a greater surface area to volume ratio as compared to this. So therefore, this will cool faster. And so if I plot its cooling curve, it would cool down really fast, and then, oh sorry, I've got too low. It should be this way at 25, because considering that 25 degrees Celsius is the room temperature, it will come into thermal equilibrium with the room temperature. It would be something like this, okay? And this would be something like this. So can you see it is taking longer? This is a steeper curve. Yes, Aisha Nadeem, good job. This graph of this smaller cube would be steeper. This will be little gentler because gradual. Why? Because it is taking longer to cool down, because it has less surface area to volume ratio. This has greater surface area to volume ratio. So more molecules are exposed to the surroundings, so they will cool down faster. And there are less molecules to cool down as well. Right? Okay, now this. Yes, I know we are out of time. Just this last one. If the ambient temperature is 20 degrees Celsius, and these again are identical cubes made up of the same substance, such as aluminum or whatever. Now, but one is at 50 degrees Celsius, the other one is at 30 degrees Celsius. Now tell me, which one will cool faster? Which one will cool faster? Myra. Good job, Aisha. Nadeem, tell me the reason. Tell me the reason. Tell me the reason. Yes, Aisha, Amna, Yusra, all your answers. Yes. And also, please, if it gains faster, it loses faster. But Aisha, I did not talk about gain. I mean, this is their starting temperature, for example. Nuh-uh. How did you know that the 50 degrees Celsius cube heated faster? How did you know that? The 50 degrees Celsius one, because it heated faster. How do you know that it heated faster? Maybe it took longer. I did not mention that the 50 degrees Celsius got heated faster. Maybe it took longer. But when it came at this temperature of 50 degrees Celsius and this at temperature of 30 degrees Celsius, from there I started timing it. So just because there is starting temperature is higher than this doesn't mean that this got heated faster. So which one will cool down faster to an ambient temperature of 20 degrees Celsius? Okay, another thing I want to mention is that, remember, the temperature of these cubes will never go below the room temperature. So a room temperature, standard room temperature is 25 or 20? 25. Standard room temperature is 25 degrees Celsius. First, you gained more heat, so it took more time trying to lose that. The 50 degrees Celsius has more energetic particles and they'll escape faster. Good job, Aisha Nadeem. Yes. Remember one thing. Remember one thing. Systems always try to minimize any gradient. I will tell you what I mean by gradient. For example, I am talking about this cube, right? This is at 50 degrees Celsius. And the ambient temperature, let's suppose, is 20 degrees Celsius. This is another, which is at 30 degrees Celsius. Now, what is the difference here? What is the temperature gradient? What is the temperature gradient? 50 minus 20 is 30. 30 minus 20 is 10. So the difference here is greater. So the temperature gradient, you are coming from 50 to 30. So, sorry, 50, 30, 20. So falling from 50 to 20 is like you're falling more. The temperature is falling more. So there is greater temperature difference. Steeper the temperature difference, faster the temperature is lost. Steeper the temperature difference, faster the temperature will decrease. Okay, look at this. These are two cubes, okay? One is at 50 degrees Celsius, the other is at, let's suppose, 20 degrees Celsius. Now the heat will move from here, from the hotter one towards the cooler one, right? Till both of them are at the same temperature. This is called thermal equilibrium. This is called thermal equilibrium. So the heat will flow from a hotter object to a cooler object till both of them reach the same temperature. This is called thermal equilibrium, right? So they are trying to come into thermal equilibrium with their ambient temperature. So this will be greater, the flow of temperature will be faster if the difference is steeper. If the difference is less, the flow of temperature will be slower. So this graph would go something like this. Okay? And this will go something like this. Okay, but both of them will stop at 20 because they are in equilibrium with their room temperature. So they should be exactly at 20. Ambient temperature means surrounding temperature, the room temperature. Ambient is just a good word for room temperature, okay? Okay? So greater the difference of temperature, faster the flow, faster the drop, sorry. Okay, greater the temperature difference, faster the drop in temperature, less the temperature difference, slower the fall. Like ऊंचाई से तेजी से गिरते हैं ना, ऐसे याद रख लो. कम हाइट होगी तो इतनी तेजी से नहीं गिरेंगे, ज्यादा हाइट से गिरेंगे तो तेजी से गिरेंगे. समझ आ गई बात? Like that. So systems try to get in equilibrium with their surroundings. No time left. I took extra time. Sorry about that. Okay, the chapter has finished, by the way, and with this we have come to an end of physics. Okay, these questions, the door canopy in figure 24.5 shows in a striking way the difference between white and black surfaces when radiation falls on them. Explain why. Really quick. Who knows? Who knows? You know, can you see this ice melting and forming icicles from the white parts, but not from the black parts? No, what? No, 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 no. No, the icicles have frozen, meaning the water has frozen at the white parts, but the black parts has completely melted. Yeah, has completely melted. You can see the wet part and it has completely melted. Who wants to answer? Who wants to answer? Come on, come on, come on. Come on. The black surface radiates more and so ice melts. You will not talk about radiation here. You will not talk about, yes, it radiates more. That is true. But right now you are explaining. So you will use that property which is explaining your answer. You have to explain why the water completely, yes, Ajwa, you will talk about absorption. Yes. No, 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 no. Black surfaces absorb more and therefore have more thermal energy, which will melt the ice, right? Whereas the white surface, now you will also compare it with the white surface. The white surface is a good reflector, so its temperature did not rise much, and therefore it is not as successful in melting the water. And as you can see, the water again froze in midway, forming icicles. Okay, question number 2A. The earth has been warmed by the radiation from the sun for millions of years, yet we think its average temperature has remained fairly steady. Why is this? Why is this? What has enabled the earth to maintain its temperature? It radiates energy back into space. So a radiation from the sun for millions of years, yet we think its average temperature has remained fairly steady. Yes, because of atmospheric layers. Yes, because if it would radiate just completely, then the temperature would fall too low, and which would not be compatible with life, right? So it is, yes, it is because of the atmosphere which like sort of blankets it and does not allow it to cool down too low. Okay. Okay, okay, then part B. Why is frost less likely on a cloudy night than a clear one? Yes, because cloud again behaves as blankets. Remember, clouds are made up of water vapors, insulator, again, so it would not allow the radiated heat, the heat which is radiated back by the earth to go too far. And so it will trap it there. And so would not allow the temperature to rise or to fall too low, right? Okay, Alhamdulillah. So according to the SOS, we have done this. We have done physics, whatever is included in the SOS, in your updated SOS. And then on Sunday, we will do, inshallah, what do you guys want to do? Chemistry or biology? Chemistry? Chemistry is okay. Chemistry is really difficult. That last chapter, quantitative analysis, it has a new concept. And according to Sayyid Nabil's SOS, Hiba beta, please, can you please kindly, from any girl from 8A, can you please kindly post the updated chemistry SOS? I want to double check if that last chapter of quantitative analysis is included or not. Okay, otherwise we will start with biology. Okay, I would recommend we start with biology because I think biology immunity chapter is definitely for sure included. They are not going to omit it. Okay, so let's start with that. So let's finish what is included first, and then if we have any time left, we can do the chapters that they have omitted. By the way, in physics also they have omitted a specific latent heat. Okay. Okay. Okay, I have taken a lot of your time. Jazakallahu khairan for bearing with me. I know you guys don't like teachers who take extra time. I'm sorry about that, but I'm trying to finish the course. You know, I'm trying to finish the course. Okay. Okay, take care. Have a great weekend. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.
My